Hello and welcome back to the Math and Physics podcast. This is episode 7, and I am your host, Parker.
And I am Ray, and we welcome you back to brand new episode. Here today we have our physics professor for both of the semesters, Professor Stephen Julian. Would you like to introduce yourself?
Yeah, hello everyone. I'm Stephen Julian. I'm a physics professor at the University of Toronto.
All right, awesome. So he was our first year physics professor, well, one of them that we had for our first semester and then a part of our second semester as well. Yeah, so let's just get right into the questions. First question, pretty easy. So how did you start liking physics? How did you get into it?
Yeah, okay. So that's it's not a completely straightforward path. It's not physics isn't something that I thought I would do ever since I was little. It came on kind of gradually. I didn't particularly like physics in high school, and I don't actually recall liking anything in high school very much. When I got to university, my plan was to I didn't really know what I wanted to do. I took quite a wide range of courses in first year, right from English to math. But in the end, I thought I was going to become a geophysicist because I had always
Oh,
liked geology ever since I was little. But
Oh,
then
cool.
in second year, for some reason, in the geophysics program, we had to take a course in quantum mechanics, and it just really amazed me. It was the first hint I had that the universe is nothing like the way that we perceive it in our everyday lives. So after that, I switched into the straight physics program, and from then on, I just liked it more and more. And then I guess by the end of my fourth year, I knew I really loved doing physics, and I went on to do my PhD. So it was a little bit of a long story, but that's how it came about.
Yeah, that's super interesting. Do you know why, um, like in the geophysics program, you had to take quantum mechanics?
It's never made sense to me, although in fact the entire second year quantum mechanics course, it was taught by a professor named Robin Armstrong, and I'm not sure why any of us had to take it. It went so far above our heads that we couldn't. I don't think any of us really understood what was going on. We just understood that it was very different from everything we'd always thought that physics was. Of course, quantum mechanics is important to chemistry, and chemistry is very important in geophysics. So maybe that's why, but I think somebody had probably put it in there without really thinking.
Right. Is this this was at U of T?
Yeah, I did both my undergraduate and my PhD at the University of Toronto.
Oh,
and
awesome.
did you take a master's course in the middle? Because we were talking to some PhD students or prospective PhD graduates that just didn't take their master's course and just directly went into the PhD program.
When I did my PhD, you had to do a master's, and there was no
Mhm.
such thing as directly into the PhD, but it was a 1 year thesis master's. So it was quite a lot of work, but yeah, I had to do a master's in between.
And what was like, okay, so I know you've already kind of described your undergraduate experience, but like, was like quantum mechanics your favorite class, or was there a favorite class in all of 4 years that you had?
Um, I would say that I had favorite classes that were my favorite classes at the time, but then I had a different set of classes that were probably most influential on me. So the ones that really influenced me, of course, the second year quantum, because it kind of changed the course of my life.
Mm-hmm.
Um, but then it wasn't until fourth year. I think in fourth year there were the classes that I liked the most. I liked most of my classes, I would say, but there were three in particular in fourth year. One of them was the advanced physics lab, and to anyone listening who's in a physics undergraduate program, it will probably be surprising to think that somebody could like a lab, because most of the labs are pretty dire in undergraduate physics, I have to say. But this one's different. This one, you spend 3 weeks doing each experiment. You really get into it. You've got the experiments are different, and what that course really taught me was that there's actually some intellectual content in physics labs.
Mm-hmm.
Whereas before that, I always thought it was just kind of mindless following a recipe. And the second
Mm.
thing that I really liked was the condensed matter physics course, which was taught by Professor Griffin. A really nice combination of abstract theory and mathematics with things that you could really think about concretely. And then I had a group theory course that was taught by this eccentric Englishman And those three courses were important to me because in retrospect, when I did my PhD, I kind of combined them. I became an experimentalist, which wasn't what I was planning before fourth year. And I worked in condensed matter theory, and my PhD supervisor was the guy who taught the group theory course. So I kind
Oh,
of combined the
wow.
three things I liked the best in fourth year in my
Wow,
PhD.
wow. So, what in all these 4 years, what was like the most challenging, I guess, exam that you had? Like any final assessment that maybe we have in our future as prospective physics undergraduates, but any like final exam or any class that was just crazy hard?
Um, I think what I found the most difficult and what most students find the most difficult is quantum mechanics, and
And that will be the
especially
second year
in
quantum mechanics?
no, the second year quantum mechanics course uh, is when I took it, it was impossible. Um,
No.
but it's not impossible anymore. But looking forward, it's a third year quantum is the course that a lot of people really struggle with um, because of the way it uses both
Mm.
calculus and linear algebra together. I guess I'm not sure why, but that's the course. If you're looking forward and thinking, what should I try to prepare for in advance? What should I spend the previous summer working on, trying to get ready for? I think that third year quantum course is probably the hardest. Um, for me, the worst exam by far was the last exam I ever wrote. It was our fourth year quantum mechanics course. And I was doing pretty well in physics by that time. And after the exam, we all came out and we figured that, um, I had maybe done the best in the class on the exam, and most I had got 30% of the marks. Um,
Wow.
but it was really annoying because the professor, we did relativistic quantum mechanics for the last month, and he told us it wasn't going to be on the exam, and then over half of the exam was on relativistic quantum mechanics, which none of us had studied. So it was not only difficult, but it was also unfair. So you can tell I still nurse some grudges about that one.
Yeah. So you talked about your lab class that you really enjoyed. Could you give us an example of like a fun experiment you did?
Um, yeah, so they had an experiment there um, to measure the magnetic properties of superconductors. So superconductivity at that time it's a subject I have ended up working on for most of my career, but superconductivity at that time was limited to materials. You had to cool them below 20 degrees above absolute zero at best. Most things were superconducting around 4 or 5 degree Kelvin. And so you got to play with liquid nitrogen and liquid helium and cool things down to really low temperatures. And they had this very old-fashioned cryostat where you could actually you could see the liquid helium boiling away in your sample. And the measurement was quite nice. It was you had a big old electromagnet, and you could sweep the field up and down. And the results the results really made sense. They fit well with the theory, but you had to work on understanding what was going on. There were some experimental details, some coils that weren't quite properly matched, and things. So it was a nice combination of analysis and actually doing the experiment was fun.
Mm.
And then there were a whole lot of optics labs, and they're always fun, I think, because with optics, they had a helium neon laser, which was really beautiful to play with. And lasers are fun in general. So I think all of the experiments I did there, I enjoyed.
And what year was that? Fourth year?
Yes, that was in fourth year. Although you can do that lab in third year as well. Some students do it in third and fourth year. So.
Okay, awesome. So I wanted to ask you about your PhD. So what was your thesis for your PhD?
Okay, so um, I've had a couple of really lucky breaks in my career, and one of them had to do with my thesis. So I decided I would do my PhD with this eccentric Englishman because I just liked the way he thought about physics. And the project that he put me on was on the magnetism of transition metal oxides. And in particular, I was working on magnetites. And I took a strange view of them. I decided that there were important fluctuations of the magnetization wasn't static, that it was fluctuating. And I did quite a lot of work on this. And I remember some of the other professors in the department talking to me about my thesis. And they told me that it was a complete dead end that I was working in. The physics I was doing was 30 years old. Nobody cared about this stuff. Nobody cared about magnetic fluctuations. And they were probably right. But then just 2 years before I was finished my PhD, high temperature superconductivity was discovered. And it was discovered in a transition metal oxide.
Oh.
And magnetic fluctuations turned out to be a key to the physics. So
Oh
suddenly
wow.
I went from being in this complete sort of dead end field where, probably my thesis, my thesis is pretty obscure as it is, but, I would never have had a career in physics except for this. So then I was suddenly one of the world's leading experts in a subject that was suddenly important. And, I was able to get a good postdoc. I went to Cambridge University in the UK for my postdoc after that, and then they hired me as a professor, and so I was really, it wasn't very sensible the way I went about choosing my PhD topic, but I was very fortunate, and it turned out to be quite relevant to
Wow.
interesting physics. So.
Yeah, so I was visiting your website on U of T, and I was reading about something that you have called Julian Group, right? And I just wanted
Yeah.
to, I was reading about it, but I didn't, once again, quite conceptually understand it. So I was just wondering if you wanted to explain a little bit more about what Julian Group is, really.
Well, I mean, it's right now my research group consists of me and three PhD students. So that's what I call the group. It's a research group.
Okay.
So it's not a group theory group or some mathematical thing. It's just a group of people. And so this is typical of the way that research works. The PhD process, I think, is a really interesting model for how you can communicate information. After working in my field for 35 years, I know some pretty obscure things, and the best way to communicate them is for me to work almost individually with students and to pass along this knowledge. So we work together in the lab, or we do calculations together. My lab is in the basement of the McLennan Physics
Hmm.
building. You can drop by and see it sometime once we all start being able to go outside again. We do high pressure experiments. So we use these things called diamond anvil cells, where you put a sample between two diamonds and press on it. So we can get up to hundreds of thousands of atmospheres of pressure on things. And what we're really looking for is novel kinds of magnetism and novel kinds of superconductivity. And
Yeah, sorry, but yeah, so I was actually just going to ask, what exactly are you guys researching? Because like I know you were just talking about the different kinds of experiments, but what exactly like is there like a purpose to this group? Like, are you trying to solve something, or is it just you guys all do research together?
yeah, no, that's a really good question. So the general area I work in is called condensed matter
Hmm.
physics. It's the biggest sort of subdivision of physics, and it partly because it covers a very wide range of things, right from device physics, people who are trying to make better, memories for computers or for phones, better transistors, right to very abstract things. So uh, one of the topics I work on, for example, is the behavior of a metal when it has a phase transition happening at absolute zero. So it has a transition from a magnetic to non-magnetic state. And believe it or not, there's a close connection between that physics and the physics of black holes.
Oh.
Hmm.
So it can be very abstract or it can be very applied. So I tend to my group works towards the abstract end of things, but we have an application in mind. So the dream of me and many people in my field is to make a room temperature superconductor.
Oh.
So that would be something that can
Oh
carry
wow.
electrical current with zero resistance at room temperature. It would be technologically, it would be an important advance. It would transform the world, I think.
Yeah.
But they're also potentially useful for quantum computing and quantum technologies. So that's kind of the grand technical goal. Whether we'll get there or not, I don't know. One of my colleagues estimated that it would take 50,000 years to discover a material that will superconduct at room temperature, but you never know. People are smart, so
Yeah.
we might be able to figure it out.
Awesome.
Um, So the deeper goal is just to understand how quantum mechanics works in materials. And the way we look at materials in my research group is that every material is kind of a universe unto itself. It has its own properties. It has its own excitations that are analogous to electrons and photons and things like that. So we try to explore each of these universes and try to understand the nature of the material.
Hmm. That is super interesting. Um, this next question is a little bit more personal, and it's about this year that just passed. So, what was your favorite topic to teach during like Physics 151 or 152?
So I hope it showed that I like all of the topics that I
Yeah,
teach.
definitely.
Um, the first time I taught first year physics, I didn't like it very much because there's a certain amount of lying involved about about how things really work. Um, and of course, in physics, we call them approximations. But uh, there are some things in first year physics, like friction and normal forces and so on, that are really just end up being left as a kind of mystery. But over the years of teaching first year physics, I've kind of found ways that I think are honest ways of teaching them. The thing I like the most is, of course, quantum mechanics. I think it's an amazing um, subject. I think that it's so interesting that the way the universe works is so different from the way we think it works, or the way it seems to work on our everyday level. And I like the way that it brings together so many different ideas from first year physics. I was going to say I like special relativity for the same reason that it's really difficult to grasp. It's again different from the way the universe seems to us in our everyday lives, and so I guess those are the two things I like the
Mhm.
most.
Well, I was actually going to say that, or at least in my opinion, in my personal opinion, not that anything was better than the other, but I just also truly believe that your quantum mechanics lectures, even though they were online, a lot of them, they were
Yeah.
super interesting because
Yeah.
I mean
Oh,
in the
thanks.
future I also maybe actually I don't know yet, I'm just first year undergrad, but I've always loved like particle physics and quantum mechanics and how quantum physics is just so drastically different from the classical world. And like I truly
Yeah.
believe that you taught that really well, and I just kind of want to thank you for that.
Oh, thank you.
The next question was, where do you think physics is headed in the near future?
Okay. Great question, but it's hard to answer because we never really know. I can tell you what the really strong trends are right now, and uh, I think that the biggest thing right now, or one of them, is artificial intelligence and using artificial intelligence in physics research, and it's being used in a lot of different areas. Right from experimental physics, particle physicists are using it to search for new particles. Theorists are using it to try to understand aspects of theory. The environmental scientists or atmospheric physicists are using it. So everyone seems to be on this artificial intelligence bandwagon these days. Whether it's going to lead to anything, I don't know, but that's one of them.
Hmm.
Uh, the second one, and I think this is important for students who are thinking about their future and wondering if they're going to be able to get a job at the end of their degree. The next one is quantum technologies, which is a topic that refers to things like quantum computation, quantum transmission of information, encoding information so that it can't be hacked, and so on. This is a really exploding field. It's a one where if you're going to contribute, you actually, I think, have to have quite a deep understanding of physics.
Hmm.
And it's also a topic where, don't tell them I said this, but I think that the engineering departments have really failed to perceive that this is becoming an important topic. And engineers are not being adequately trained in quantum mechanics to be able to contribute to this. So I think that this is a an area of really intense research right now. Governments all over the world are throwing huge amounts of money at it, and they're hoping that we're going to be able to make quantum computers. So I think that quantum technologies, and it's not completely unrelated to artificial intelligence either. And then a similar trend is in nanofabrication and being able to make things smaller and smaller. As they get smaller and smaller, quantum mechanics becomes more important, more and more important, not just for sort of solid state devices, but also for optics. So there's a lot of interesting things happening with nanofabrication these days.
Mhm.
And then in the particle physics regime, just as an interested observer, dark matter seems to be the topic that everyone is most excited about right now, where they think they're going to be able to make the most progress. There's a lot of theoretical work there, and there's a lot of really interesting experiments being set up all around the world to look for massive weakly interacting particles and things like that. So I think those are some of the trends. Computing, I guess you shouldn't. It's impossible to overstate how important computing is to modern science and modern physics. So it's transformed all fields of physics, and as computers get more and more powerful, it's possible to do more and more interesting things, and that includes, with atmospheric physics and geodynamics, and experimental physics has been transformed by computers. When I was doing my PhD, if I was doing a measurement, I had to sort of sit next to the experiment, sometimes for days at a time, writing down numbers or punching them into. We had fairly primitive computers. And now a computer does all that babysitting and changes the temperature and ramps the magnetic field and things. And it offers everyone a chance to think about things. So computing in general, I think, is an important.
Talking about computing, I was just wondering if in your field is there a quantum entanglement also involved?
Yes, yeah, absolutely.
Perfect. So I actually have just so because you were talking about quantum computing and stuff, I was just wondering if you know anything like about quantum entanglement because I've been reading, the future of quantum computing. The entire point of it is so that if we can entangle particles, we can, transmit data at faster than light speed theoretically. So I was just wondering if maybe you would know anything about quantum entanglement and how that can help the future in quantum computing.
Yeah, I think the main point is that when you entangle two bits of uh, two qubits, then when you carry the computation forward, there's a lot more information contained there than in just the usual classical computer where something's a zero or a one. And
Mhm.
the real um, struggle now is to find systems that you can actually implement this entanglement on, uh, whether it's going to be spins embedded in a solid, these nitrogen vacancies in diamond, or
Mhm.
whether it's going to be done optically. There's some progress being made with superconducting qubits and so on. So the difficulty, it's been a little bit difficult to explain what entanglement is to someone who doesn't know what entanglement is. But the real battle is to get these things that can behave quantum mechanically and can talk to each other, and the talking to each other can be switched on and off the way that you need to. So the field I work in fact, the problem we have is that things are too entangled. There's just massive numbers of particles that are entangled with each other, and so it's not so clear that what I do is going to be useful for computation, but for understanding quantum entanglement, for sure, it's a very relevant topic, and I think that it's a for me it provides an interesting way of thinking about the physics that I'm doing.
And do you think that it is like possible in the near future that it can actually exist like a fully fledged quantum computer? I'm not saying like a laptop, but like a quantum computer that doesn't require the space of 10 buildings. Like do you think that it is actually a possibility in let's say the next 50 to 80 years?
Oh yeah, yeah.
Oh,
Well,
okay.
they already have. Google already has an IBM already have quantum computers. They're not. They don't have very many bits, but they have enough that they can actually do things with them. And I know there are lots of objections, and I've voiced some of them myself over the years to quantum computers. The troubles with maintaining quantum coherence over a long enough time to do a calculation. But one thing I've learned, I've been doing physics for a long time, and I mentioned it before, is that people are really smart. And things advance, in most cases, things advance much more rapidly than you think that they're going to. I mean, with quantum
Uh,
computing, I remember when it first came out and they said, well, with 100 qubits, you can do a useful calculation. And then they realized that they had to have error correcting codes. And then it was, well, with a million, you can do something useful. And for about the first 10 years of quantum computing, they got further from their goal, not closer, because they kept realizing they needed more and more. But I think they're getting better and better fidelity with their quantum computers, and I do actually think that they will be able to build something pretty useful in the near future.
So talking about computers, um, I wanted to talk to you about simulation theory. So I know you said you didn't know a lot about it, but I can give you
Yeah,
um, my little statement here. So because we live in a world where we have computers that can simulate, like they can have games and run programs, and now we're moving into like VR, where like video games are getting closer and closer to real life. And so the idea is that because we live in a universe where we can, somewhat simulate life, will technology get so good to the point where the simulation can appear in a simulation itself? And then what you have to think about is, well, if that's possible, then maybe we're in a simulation. And um, I forget who said this, but I think it was Elon Musk. He said that it's more likely that we are actually in a simulation than not.
I see. So, and did he say why the simulation was created? It was just that aliens were bored and they wanted to have something to do, or
Yeah, I mean, it could really be anything, but basically, because there's kind of like an endless loop of just simulations and in simulations, that um, the the thought
yeah,
that we are the very first layer is
I see.
very, very unlikely.
Well, actually, I, I've read a little bit about this. I think it's an intriguing idea. It would explain some things, like why math works so well, for example, um, and it might explain why, at some level, they left things to probability. Right, is because it becomes just too tedious to compute everything. So let's let probability play a fundamental role. I don't know. That's a fun idea. I guess the
Hmm.
computers would have to be a lot better than our computers to simulate all of this.
Yeah, the idea is that there's no real way to actually prove it,
Mhm.
but it's just kind of an idea to, like, you can't disprove it, so maybe it's
Yeah,
true.
yeah, yeah.
There's no real way to know.
Yeah, so basically, I think also what Parker's kind of also trying to say is how close do you think we are to like the technological singularity? You know, because I don't know if that's a direct question to what he's asking, but it's kind of my own question that I just made from it, because it's kind of like if we can simulate a real human's brain inside of a computer, that's pretty much like saying that this person that's inside the computer is a simulation. So if we can
yeah.
say that, and if we achieve technological singularity, then we can say that we can simulate other people, and hence we could possibly also be simulated. So the real question, or as I said, a small other part of the question can be, do you think that we're close to achieving this technological singularity in the sense where we can simulate a real person, a real human brain in a computer?
So I guess I have two parts to this answer. To me, it feels like we are close.
Mm-hmm.
Um, but whenever suggest this to either someone in computer science or to my wife, who is a cognitive psychologist, they think I'm nuts. So people, the people who have more expertise in this field than I do, don't think we're close. But to me, it feels kind of like we are. So, for what it's worth, I guess that's how I would answer that question.
All right, great. We're on 33 minutes now, so I think we could end it here.
I think we're good. Yeah.
Okay, cool.
Professor Julian, thank you so much
That was
for
fun.
being with us on this podcast. Thank you so much.
All right, you're welcome. Have a great summer.
Thank you so
Yeah,
much.
you too. So this was the seventh episode of the podcast. We've got new episodes coming out every single 3 days. I think we decided that.
I think it's like a 3-day interval. Yeah.
Yeah. All right. Awesome. So yeah, we'll see you guys on the next episode.
Okay, perfect. We're signing off. I am Ray,
And
and
I'm Parker.
we will see you soon.
All right. Bye.